Hello, and welcome to Chapter 1 of The Good Earth for the Keweenaw Bay Ojibwe Community College's Geology class. In this lecture, I'm going to go over, as is shown here, Chapter 1, and provide a brief summary of the slides and what the chapter is trying to entail. If you go check the online resources, these slides should be available to you. And of course, if you have any questions, write them in the comment section down below. I'll do my best to answer them. Or if you prefer, shoot me an email. My email should be known to you and should be available on the syllabus. So let's begin. In this chapter, we're going to cover these four main subjects: Earth science and the system, the scope of Earth science, doing science, and science in society. This chapter is, in essence, your standard introduction to science that every introductory level science class has. You understand what science is before we can talk about the science. So, Earth science and the Earth system. What does a scientist do? Well, in general, scientists seek to, 1, identify and measure natural processes and phenomena. 2, understand the natural processes involved. 3, monitor these variables over time and predict future trends or events. And 4, engage citizens to make their representatives in using this information, engage citizens and their representatives in using this information to make effective decisions and meet society's needs. So let's dig a bit deeper in each of these sentences. The first part there, identify and measure natural processes, is the field work of science. All science involves dealing with and collecting data, right? You probably talked about the scientific method when you were in high school, for example. Step 1 there is the scientific method, the lab stuff, the wear the coat, all that stuff of science. But just collecting the data is not the end of the conversation, right? Understanding the data, or part 2 there, is also very important. And then using that understanding to interpret and provide some benefit, step 3, is kind of where it all comes together, right? This is the prediction of natural disasters. This is the creation of new technologies, the engineering, stuff like that. And of course, part 4 is a bit more contentious nowadays, but that is taking the lessons you've learned from steps 1, 2, and 3 and making things better for humanity as a whole. So let's link Earth science to this conversation here. This is a picture of a glacier. In case you're wondering about scale, that's a mountain you're looking at. So this is a very, very, very large chunk of ice, this glacier here. Something we know, many glaciers are melting faster now than they have in the past. Glaciers hold a bunch of water, glaciers hold a bunch of air, carbon dioxide, stuff like that in them. A glacier melting is, in general, not a good thing. And as we said before, as the glacier melts, all that ice will then go and enter the waterways. And what could possibly happen? Well, sea levels may rise. And if sea levels rise, things on sea shores become in danger. This example here, all these arrows show the possibilities of the sea level rise and how it can affect stuff. Notice Hawaii covered in arrows, right? Louisiana, that's the Mississippi Delta there, those red arrows in the center, covered. A lot of damage can happen if you increase the sea levels by melting the ice that's in glaciers. So what do you do about this? Well, if you can't stop melting the glaciers, you need to construct ideas to deal with the rising sea levels. This glacial melting idea here is steps 1 through 4. Identify and measure natural processes. Glaciers are melting faster. Understand the process involved. They're melting faster by and large because temperatures are rising. Ice melts in hot weather, right? Monitor and predict the trends. As glaciers melt, sea level will rise, causing issues here. Engage citizens and their representatives. If sea levels rise and all those arrows suddenly become danger zones, what can we do about it? That's an example of Earth science directly related to these 4 major processes of science and scientists in general. So, the scope of Earth science. Earth science is the investigation of interactions among the four components of the Earth system, or the four spheres, as we commonly call it. The atmosphere, the air, the hydrosphere, water, the biosphere, plants and living things, and the geosphere, the rocks themselves. Geology and earth science isn't necessarily just studying the rocks, but studying the interplay among the entirety of our planet. And of course, you can also talk further about interactions with the exosphere or things outside of Earth, such as the sun, space, etc. So, how do you interact with the components of the Earth system? In the atmosphere, for example, what is the atmosphere and how does it play? Well, for the example of the glaciers from before, as the atmosphere warms up, it's going to affect things that are directly related to slight changes in temperature, such as glaciers. Hydrosphere, right? That is, of course, the glacier, but also the water around that and the clouds, all the water. Those play a big impact. As we dig deeper into this chapter, you can see water is, well, for most scientists, water is the key driving force of anything and everything that goes on. Biosphere, of course, that's you and me and the plants and the bugs and the bacteria and everything else. Again, crucial, right? Without the biosphere, we don't exist because we're the biosphere. But the biosphere also plays a big role in your classic hard geology science. And again, as we go further in this class, we'll see those interactions grow. And of course, geosphere, the rocks, truly the best part of everything we do. Look at that. That's so pretty. So let's go back a little bit here. Science is, as we discussed, a process of discovery that increases our body of knowledge. We learn more when we do science. Information that can be learned, much of it is waiting to be discovered. So, well, there's a lot that we know about science. There's untold amounts more that we have yet to discover. Curiosity and creativity of scientists in the search for answers to critical questions. Science is all of these things. Science is the process, the drive, and the acknowledgement there's so much more to do. In this class in particular, and in general, it's important to stress that science is not listing information. Science is so much more than the book in your hand. Science is the whole process of getting there and the process of it going forward. How do Earth scientists collect their data? Well, Earth scientists, as again, we're going to talk about through this class, is a very, very broad field. But in general, the most common way to collect a measurement to learn something about the environment is to go out there and do it. Direct measurement, samples of data collected from field locations. A good example of this would be going out to a rock outcrop, tapping off a piece of rock. You now have a rock that you can study. Or going to a stream and finding a fish, or measuring the water current, or watching the clouds move, or an astronomer looking through a telescope. Direct measurements are a primary way that scientists can collect data. You also, of course, have indirect information. This is data that is collected and then used for interpretation of something else. For example, and again, everything we're going to talk about here is very surface level. We're going to get into more detail later on in the classroom. Measurements of magnetic susceptibility used to determine rock type present on the ocean floor. You can study parts of a rock, such as its magnetic properties, and then use that magnetic property data to learn other things about the rock. And of course, the third and very equally important way that scientists collect the data is modeling. If we know how something works, we can use the math of how that works to learn more about it. If you want to study the interior of the Earth, you can't physically go to the center of the Earth because Earth is really big and the center is really hot. So we take modeling, we take data such as seismic data, and then we add that math into our computers, and we can use that math to interpret and derive tangible, real information. Or in the example given here, wave tanks. Want to study water? Instead of having to go out to the ocean, you can simulate water very accurately for your measurements. Again, here, techniques, these technicians are using an instrument made of different bottles to collect samples of ocean water. Example of direct measurement. This wave tank here, gigantic wave tank here, simulates tsunamis generated by earthquakes. So you can study the effect of how the water, you can test how something you build will stand up to a tsunami, for example. So to do science, you need observations, test a hypothesis, one or more predictions based on the hypothesis. This, again, is just basic scientific method. In reality, and again, we'll get to this as we go through the class, the scientific method is very robust, very varied, and ever-changing. There is not one scientific method. There's a scientific method that you're using to accomplish the goal you want to accomplish. And it's cyclical. Again, we'll get to all this as we go. So let's talk about a couple of definitions here. A hypothesis. A hypothesis is a testable explanation that can be verified or falsified. Verified essentially means correct. Falsified means incorrect in simple terms. Hypothesis is not, I'm going to stress here, an educated guess. Hypothesis has a reason for it. It's not, well, I just think, right? That's not hypothesis. Hypothesis is an explanation that you have a reason to believe. And if it's verified true, excellent. If it's falsified, it doesn't necessarily means that's wrong in whole. It just maybe needs to be altered or manipulated a little bit. Observations. These are facts, measurements, information, or data. These are the parts, the Lego pieces, if you will. And the prediction is the statement of which will happen in a given situation or set of circumstances. Prediction is what you think prediction is. What's going to happen? If I build this structure and these waves hit it, this is how the structure will respond. That's a prediction. And the three are all very connected, of course. So, which of the following statements is more accurate? I'm more or less going to skip the science concept tests for this style of presentation because you're just going to listen to me give the answer. You're going to have pause it. And by and large, they're pretty straightforward. So a lot of these will be discussed in the homework assignments that we do. If you find these science concept tests interesting, I will be saying when we get there, I won't just skip them. So you can pause the video and try to answer the question if you want. Moving on. Hutchinson gas explosions. Gas explosions in Hutchinson, Kansas, linked to gas storage facility. Scientists hypothesized gas traveled to Hutchinson in fractures in underground rock layers. What's going on here? So you have explosions in Kansas, and the people in Kansas are like, why do we have gasoline exploding all around us? This doesn't make any sense. Well, scientists looked at this problem. They said, well, the gas had to get there somehow. It's not simply like the gas station's blowing up. So how could gas get there? Well, we are drilling for oil outside of this town that's having these issues. Perhaps the gas is getting to the town in some way, shape, or form. Maybe some sort of fracturing or cracks in the underlying rock underneath the city allowed the gas to travel, get to Hutchinson, where it ran into issues. A practical example of the use of science to resolve a dangerous situation. Scientific discovery, the scientists found additional hazardous gas concentrations, and they used their knowledge as geologists of the existing rock in the region to predict potential routes of the gas. As said there, we know that there's gas out here, and we know the type of rock, in this case, dolomite, can have fractures that gas can travel through. So we have a hypothesis of this is what's going on. And it is a testable prediction because if the gas from the well there at the Yagi gas storage facility has no way to travel to Hutchinson, then we have falsified our statement. However, if we can verify that the gas from the Yagi gas storage facility is traveling to Hutchinson, excellent. So the hypothesis can be tested by either using inductive or deductive reasoning. Again, I'm stressing here, Science is not that simple chart that was on your wall in 9th grade science class. Science is a gigantic web of possibilities and avenues to take and paths to discover. So when we're going to test hypothesis, we can use inductive or deductive reasoning. These two are different, but both equally valuable. Inductive reasoning is general conclusions from specific observations. This involves, for example, recognizing patterns in data. Deductive reasoning is, well, the reverse, specific conclusions from general principles, such as the math behind something, laws, principles, what have you. And as said here, both are used to establish what you begin with. You take your observations, you draw hypotheses from those, or you take your hypothesis and find observations that support it. Both places get you to experiments or additional observations that result in a theory. Inductive reasoning example. 3 massive hurricanes caused significant damage to the United States in 2005. Hurricane Katrina, Hurricane Rita, and Hurricane Wilma. Big hurricanes, right? Therefore, massive hurricanes with low air pressure around 900 millibars or less will likely cause large amounts of damage if they hit landfall. That makes sense. I have specific examples of big earthquakes causing a lot of damage, so I can conclude a big earthquake measured by 900 millibars of pressure caused the problem. I have a prediction made off of this inductively reasoned observation. Deductive reasoning example along the same lines would be all hurricanes form as low pressure systems over oceans. Hurricane Sandy is forming in the Atlantic. Hurricane Sandy must be in a low pressure system. Again, I'm not talking about hurricanes in general. I'm talking about specifically Hurricane Sandy. Notice here, I am studying this one with a hypothesis, and then observation is second, whereas here I have the observation and then my hypothesis. But we still get there. Here's another science concept test. Feel free to pause if you'd like to go through it. Same song and dance. Feel free to pause if you think that is relevant, if you want to do this. So science follows some basic rules, right? That loosely define the scientific method. Again, calling them basic rules is true, or all scientists want to end in some sort of prediction or useful information, but the path you get there is rarely, if ever, straight lines. So, scientific, couple things to remember. One, a scientific hypothesis is tentative and can change. In fact, they almost always change. You don't really guess right the first time. Otherwise, science would be easy, and science is not easy. 2, a scientific hypothesis should be predictable and testable. Test results should either support or falsify the hypothesis. If you make a claim, the claim should be able to be true and should be able to be false. That's a big part about science, is you can be wrong. If you can't be wrong, you're not really making a scientific claim. 3, a scientific hypothesis is based on data from empirical or tangible examples, observations, and experiments. So you need to have something there for your science. It could be a model, or it could be a chunk of rock, right? 4, a scientific hypothesis offers a well-defined natural cause to explain a natural event. Science doesn't really do a good job of explaining things outside of nature because science works within nature. That's what that's saying. An example of an emergent hypothesis, of course, would be global warming. Big hot button issue, right? Average temperature of Earth is increasing due to the buildup of greenhouse gases in the atmosphere. Cool. Tentative example. Estimates how much temperature is increasing. How much temperature is increasing will change. Meaning, as global warming continues, how much faster will the globe warm? Empirical measurements would be those actual temperatures. Predictable hypothesis would say Okay, if we adjust carbon dioxide levels, how will they adjust temperature levels? And then, of course, the natural component. We have climate records of about 500,000 years that show parallel changes between temperature and greenhouse gases. We know in the past, when we've had different amounts of greenhouse gases, we've had likewise different temperatures. So we can connect all four of these sciences together to create a robust, a powerful explanation. Not all science is good science, of course. This can be a particular concern when reading about science in popular media. This is a very fun topic to get into. Oh, okay, sorry, I thought I had to do something. Back to the lecture here. A common pitfall when discussing science is, first of all, attacking scientists. In general, you really want to focus a conversation about science on what the science says. The political or religious affiliations of the people involved don't really have any bearing on what you're talking about. And then secondly, you do have an issue of misuse of authority with science. There are a few very well-known scientists out there. Neil deGrasse Tyson, Richard Dawkins would be examples. Stephen Jay Gould, right? You probably heard of him. Stephen Hawking, of course. You can go further back in time, Einstein, Darwin, stuff like that. Just because you are an authority in a subject doesn't mean that you have the final word in science. And that can be another issue with popular media and what it discusses. So things to keep in mind. A third example of bad science is cause and effect. Correlation does not mean causation. If you have two things that are happening together, that doesn't mean those two things are necessarily related. You need to prove that they're related in order for them to be related, right? There's lots of hilarious websites about this, correlating like Nick Cage movie releases with bird deaths in like Bolivia or something like that. I mean, there's lots of meme-worthy correlation causation conversations, but it is a real issue you can have. And of course, poor statistics. There's a very famous quote: "There's lies, damn lies, in statistics." Just because you have the data, if you don't know what the data means or how to read the data, you can pull out incorrect statements from it. Or your chart of your data can be made poorly to achieve different results. Again, Google this sort of stuff. You're going to find lots of newscasts using data horribly to try to create a point, right? So things to watch out for. Pseudoscience, that is a fun one. Oh, there's a misspelling there. I didn't even notice that. I apologize. Pseudoscience is a system of theories, assumptions, and methods erroneously regarded as science. Pseudoscience is a touchy issue because a lot of times when you discuss pseudoscience, you are discussing it with someone who has a very personal relationship with it. So we're not going to dig too deep into this, but confusing pseudoscience with actual science is a very important topic to discuss. A good way to tell science from pseudoscience is how much of this conversation is going down, how much steps is there, how much practical work is there behind the science before you get to the conclusion. If you don't have a lot of observation and conversation and altering of your theory before you get to the end, that might mean that there's not a lot of work going into the answer. And that's something to watch out for. So here's another science concept test. If you'd like to take it, please pause the video. And again, actually, I'll go back here if you want to pause. So A, B, C, and D are all the same science concept test. And then here's another science concept test if you'd like to pause and do it. Again, I'm skipping over those because I want the conversation to evolve more so around the assignments and what goes on there. So, all right. So fertility statues and the scientific method. Let's do a let's have a conversation about this. Employees at Ripley's Believe It or Not Museum in Myrtle Beach, South Carolina, declare that female visitors who have come in contact with a pair of African fertility statues have become pregnant. The statues from this tribe in the Ivory Coast stand near the museum's entrance. Some visitors have told the museum staff they gave birth 9 months after touching the statues. The museum notes that couples travel from far away as Texas to rub the statues. Interesting. This is an example of correlation and causation, right? People are giving birth from touching these statues. The statues are claimed to be fertility statues. Therefore, the statues are causing pregnancies, right? What's going on with this conversation? What's going on with this paragraph that makes you think poor science? Feel free to pause the video here. Feel free to read it. Write your comments down below if you want. There's a lot going on in this that if you know what to look for with bad or pseudoscience, you can point out a lot of glaring inaccuracies here. A couple steps to go through in case you need some help with that process. Again, it's worth your time, I think, to actually dive into this, dive into this chapter and go over these questions. See if you can figure out what's going on. So let's talk science and society here. Earth scientists' roles in society. What does a Earth scientist do for humanity? Well, one big thing an Earth scientist does is they alert people to Earth processes or hazards that may cause damage or loss of life. Volcanoes would be a good example of that. We saw pictures earlier about tsunamis, earthquakes, right? All of these things are super powerful and cause massive, massive damage, loss of life. Earth scientists are the people that study this phenomena and can best guess what's going to happen. Provide for material needs for society by managing natural resources. If it can't be grown, it has to be mined, right? Everything around you probably has some mineral component to it. The computer you're watching right now, full of minerals that a Earth scientist found and helped excavate and process. Earth scientists protect us from activities that may endanger the natural environment. This is the global warming conversation. This is mudslides and stuff from over farming, all of that. Again, everything we're talking about here, we'll get into more detail as we move forward in the chapters. And of course, to ensure the future of humanity from global threats such as climate change or an asteroid impact. If you've never seen the movie Armageddon, you really should. It's a fantastic movie. Which types of natural hazards are most significant for the region you live in? That's a good question, right? Where you live has very different things to be afraid of. For example, you live down in New Orleans or Jacksonville, or you have hurricanes you need to worry about. We did a slide a couple minutes ago about gigantic hurricanes hitting the American Southeast. However, if you live on the West Coast, you don't have hurricanes as an issue in that part of the Pacific, but you do have earthquakes. What causes an earthquake? We'll get to that later, right? You look up near us in the Kappa country up there, what natural hazards do we have to deal with? We don't really have hurricanes, do we? We don't really have tornadoes. What do we have? Earth scientists' role in society. As said before, alerting people of issues, both prevention, if possible. For example, preventing flooding is a very important component of a Earth scientist's job. If you know an area is going to flood, what can you do to either remedy the flooding or build to protect yourself from it? And of course, adjustment, regulation codes for earthquakes, for example. I think that's a typo there. The hydrogen formed soon after the Big Bang. That's a typo. I apologize. Here's a science concept test if you'd like to pause the video. Natural resources, as we talked about before, if you can't grow it, you got to mine it, right? Electronics use massive amounts of copper, are caused by large burn oil and burn gasoline or lubricated by oil, right? Most of our houses are heated by some natural resource. So that stuff in lot very much far and wide involves geology. And even non-renewable resources such as water, and it's supposed to be wind, not soil. Sorry about that. Even non-renewable resources, earth scientists fall in the purview. If you want to build a wind farm, you need to know what wind currents are. That's an earth scientist will tell you that. A sustainable society, of course, is a large goal for most modern nations. We don't want to run out of the ability to heat our house in 150 years, and then we're going to have a big issue, right? Managing these natural resources, of course, is important. What's the pattern of nightlight suggest about global use of energy and other resources? There's lots of electricity in very small sections of the world. Of course, the Sahara Desert and the Himalayan mountains are going to have electricity, but South Central Africa there's lots of population there, not a lot of electricity. These are the conversations that should be had. Of course, protecting environments and protecting and supporting natural environments is a good thing that scientists do. Here we have a picture clean up the deep water horizon oil spill off the Alabama coast. If something does happen, how do you remedy that situation? Humans and earth scientists play a key role in that conversation. And of course, Armageddon, fantastic movie, well worth your time. Who knows? Maybe there's some extra credit in this class if you watch Armageddon and write me up a nice little report about how much you love that movie. It's such a good movie. Excellent soundtrack, too. Here's another science concept test. If you choose to do it, please pause the video. And there you go. Here's a nice little concept map where you can fill some stuff in for you. I actually believe this is an assignment I'm giving you. So here's a visual for you. What can you learn about the Earth and how can it play? For example, on the right-hand side there, study Earth to learn more about something that asteroid impacts threaten us for. How can an Earth scientist, what can Earth scientists do to help us in case we're threatened by an asteroid impact? And the scientists do that nowadays. There's people actively wondering, how do we solve, and if an asteroid is going to collide with the Earth and we don't have Bruce Willis available to go up in the space shuttle at that moment, how do we solve an asteroid without Bruce Willis? Lots of people are wondering that exact question. And then here's that conversation we had earlier about the interactions between all the different spheres. Again, I think this is an assignment I give you, but each of those A, B, C, D, E, F, G, each of those letters, can you explain the interaction in that way? Hydrosphere down to biosphere, for example, F would be raining on plants, right? You rain on a forest, the biosphere sucks up the water and the plants drink the water. That's an example of F. But what about E? And there you go. There's chapter 1 of The Good Earth for Keweenaw Bay Ojibwe Community College. Thanks for listening. And again, if you have any comments, feel free to leave them down below. Or if you prefer, email, talk to me in class, whatever works best for you. Thanks for listening. Take care.